guys, how's it going? Hopefully, you did well on your exam, and today we're starting with physics, and we are going to be looking at calculations involving gravitational fields and electric and magnetic fields. But today we're going to start with gravitational fields. Okay, we are starting with this page in your book, page 3, okay, and there's a formula here which calculates gravitational field strength. So basically, what is a gravitational field? A field, right, is anything that has, I'll just show you. If this is Earth, a field is like invisible, okay, so there's this invisible field around Earth, and it's a force. Okay, so that's what a field is. It's invisible and it's a force. And we say that gravity is a field because gravity is invisible, okay? So you guys, if you jump up, gravity pushes you back down, right? You can't jump up and keep jumping higher and higher and higher because gravity is this invisible force, this field that keeps us on this planet. So if this is the planet Earth, here's the gravity. Okay, you can see the gravitational field that I'm drawing on the Earth, and you can see that the gravity is pushing in, right? So fields have a direction, right? So they're vector, like if you remember from Science 10, if there's a direction, then it's a vector quantity, like north, east, south, west. Those are examples of vector quantities because they show direction. So you can see this shows direction because it's pointing in. So this is a vector quantity, right? Gravitational fields. Anyways, as you can see, if you look at my field diagram with these arrows, you can see like right here, the distance between these two arrows are closer than the distance over here. You can see the distance is further apart. And that's because the closer you get to the Earth, the stronger gravity is. And the further away you get from Earth, the weaker the gravity, right? The weaker the gravitational field. Some things about gravitational fields that you guys got to know is like the bigger you are, the more gravity you're going to generate, right? So if you increase the mass, you're going to increase the amount of gravity, right? That will produce. Like if you're looking at yourself, you have mass, but you're really small, right? Because you have mass, you're going to have a little bit of gravity, right? Which means that you also have a gravitational field where you're pulling things towards you, but because you're so small, your gravitational field is going to be really, really weak, right? But if you compare it to like the Earth, like imagine here's the Earth and imagine this is you, you're like tiny speck. The Earth is way bigger than you, so it's going to produce a way bigger gravitational field than you do. And we calculate gravitational field using this equation. So the equation that I'm using is little g is equal to big G m r squared. That is my gravitational field formula. Okay, where this is gravitational field strength. Okay, that's what that means, gravitational field strength. R is the radius. Okay, now big G is a constant, okay? And big G is actually given to you guys in your data booklets. I just had the data booklet, and it shows you right here in your data booklet on page 2, okay? And it says that the gravitational constant is 6.67 times 10 to the negative 11, and then there's this big unit attached to it. So the constant is 6.67 times 10 to the negative 11 newtons per meter squared over kilogram squared. And then this M stands for mass, which is in kilogram, and radius is measured in meters, okay? So this is the formula that you guys use to calculate how strong the gravitational field is around an object. You can actually calculate your own gravitational field by putting your mass in here. Like if you weigh 50 kilograms, you put kilograms in here. And your radius, let's say you're 1.5 meters tall, you'd be 0.75. Like your radius would be half of you, because a radius is like half a circle. So that would be your radius. And so there you have it. Okay, let's use this equation and in context. So what we're going to do is I'm going to try a practice problem which is in your book. And it is this on page 6. Okay, so let's try it. Determine the gravitational field strength of the Earth acting on a satellite orbiting at a distance of 12,370 kilometers away from the Earth's core. Okay, so here we go. Here's the Earth, okay? And you want to determine the gravitational field strength of the Earth, and here's the satellite. So here's the satellite, and it is orbiting a distance. Here's the Earth's core, and the distance that it's orbiting is 12,370 kilometers. Okay, so you can see that the radius is given to you because this is the radius, right? Now, it's telling you, you know your formula is little g is equal to big GM divided by r squared. Okay, now let's take a look at everything that we know. Do we know G? Yes, because G is a constant. Remember, that's what's given to you in your data booklet, right? It tells you what G is right here, 6.67 times 10 to the negative 11. So you know like G is equal to 6.67 times 10 to the negative 11. And then mass, is mass given to you? Well, that's another thing your data book provides, okay? Your data book tells you what the mass of the Earth is, and it actually tells you the radius of the Earth, the mass of the sun, gives you all of this, right? So you now know the mass of the Earth because it's given to you. So the mass of the Earth is going to be 5.98 times 10 to the 24 kilograms. Okay, now R, you already know what R is, but R needs to be measured in meters, and they gave you R in kilometers. So you got to convert kilometers to meters. Okay, so how do you do that? If you have 12,370 kilometers, how many meters is that? Well, times that by 1,000, okay? So 1,000 meters is equal to 1 kilometer, okay? So that's like a basic unit conversion. 1,000 meters is equal to 1 kilometer. So that means if you had 2 kilometers, that would be equal to 2,000 meters, right? You times that by 2. But now you have 1,370 kilometers, so you got to times that by 1,000 to give you 1,237,0,123 meters. So there you have it. So now you have meters, you have your gravitational constant, big G. Sorry, this should be big G. You have your mass, and now you can calculate your gravitational field strength. So that's what we're going to do together. Okay, so let's just calculate our gravitational field strength together. Okay, so the gravitational field strength is equal to 6.67 times 10 to the negative 11, that's our constant, times the mass. The mass of the Earth, remember, is given to you in your data booklet, 5.98 times 10 to the 24th, divided by the radius, which we had to convert to meters, 1,237,0,000 meters. And remember, it's radius squared, so you got to square that bottom number. Now, when you plug this in, you're going to need a calculator, right? So here's like my TI-83 calculator that I have, okay? And when I plug it in, okay, this formula, I'm going to go, okay, 6.67 times 10, right, to the power of negative 11 times, then put it in brackets, the 5.98 times 10 to the power of 24, bracket. Okay, so this little arrow that's up indicates to the power of. You get this answer, 3.988 times, and then divide that by 1,237,1,234, right? Square that number because it's radius squared, and your answer is 2.61. Okay, so your answer then becomes the gravitational at 2.61 Newton per kilogram, because that's the unit for gravitational field strength, right? And there you have it. You just calculated gravitational field strength. So one thing you guys got to just kind of remember is the units always have to be, for radius, has to be in meters. The mass always has to be in kilograms, okay? And that you have to convert your unit accordingly to get the correct answer. Now, we're going to do another question, because sometimes it gets a little bit more complicated. So let's try this, where you have to determine the mass of a planet, okay? It has a gravitational field strength of 7.12 newtons per kilogram, and the radius is 1.37 times 10 to the 7 meters away from the planet. But you don't know what mass is. That's your unknown. So that means you got to look at your equation. So little g is equal to big GM divided by r squared. Okay, well, you know what big G is because it's a constant and it's given to you. So you know that that's 6.67 times 10 to the negative 11. This you don't know. This you do know. It's given to you that the radius is 1.37 times 10 to the 7 meters. And little g is also given to you as 7.12 newtons per kilogram, okay? So because you don't know m, we have to solve for that, right? We know everything else has been given to us except for m. So then how do you isolate for m? Okay, well, we'll do that together. G is equal to big GM times r squared. Well, we got to get rid of whatever's on the denominator or the bottom first. So this is big GM divided by r squared. So I times both sides by r squared to get rid of the r squared there. So now I have r squared times G is equal to big GM. I need mass to solve for mass. So this is big G times M. So I got to get rid of the big G by dividing, right? That'll cancel that. And guess what? I get mass is equal to r squared times G over big G. And there I just solved my equation. And now I can solve my equation because I solved for mass, right? So that means mass is equal to r squared 1.37 times 10 to the 7 squared times my gravitational field strength, which is 7.12, which is given to me, divided by big G, which is 6.67 times 10 to the negative 11. And then you got to plug this into your calculator, okay? So again, we have, okay, so we got to go 1.37, 1.37 times 10 to the power of 7. Okay, and you got to square this. Got to square that whole thing. Gives you 1.8769 times 10 to the power 14. I times that number by 7.12. And then I divide it by the brackets, 6.67 times 10 to the power of negative 11. And I get an answer of 2.00. And that is correct, okay? So now my mass is 2.00 times 10 to the 25 kilograms, and I have that correct, okay? So there you go. Now the last time, what if they ask you to solve for radius, okay? If they ask you to solve for radius, so let's say the radius is your x, you don't know what it is, the mass is 1.58 times 10 to the 25th, and the gravitational field is 6.11 newtons per kilogram. And you don't know what x is, okay? So, but you're given this formula, G is equal to big GM r squared. So again, you got to get rid of the denominator, which is your r squared first. You always get rid of what's on the bottom first. So you go r squared, that cancels. Now you have r squared times G is equal to big GM, okay? Now you want to solve for r, so you divide. This is r squared times G, so divide both sides by G. And you're going to get r squared is equal to big GM divided by little g. Okay? And then to get r by itself, you square root this whole thing. So you end up getting r is equal to big GM divided by little g. Square root. Okay, then that's how you solve for r. You need to isolate. You got to do your formula and isolate for r. And so that means if I want to solve for r, well, r is equal to big G, which is 6.67 times 10 to the negative 11, divided by the times the mass, 1.58 times 10 to the 25, divided by little g, 6.11. Okay, and then square root the whole answer you get. And that's how you figure out r. So I can do it on my calculator. 6.67 times 10 to the negative 11, right? Times bracket 1.58 times 10 to the power of 25, bracket divided by 6.11. I get this answer. Then I gotta square root it. So second square root, second answer, enter, and there's my answer, and that is correct. Okay, so I get this big answer 13133. 131333208. So I can make this in like, here's like, imagine this is my decimal and it's 0.99. If I move the decimal over 1, 2, 3, 4, 5, 6, 7, I can then make it 1.3 times 10 to the 7. Okay, meters, because I move my decimal places 7 places, and I'm moving it to the left. So when I move it, the decimal to the left, it's always 8 positives. And that's how I do that. Okay, so now I gave you how to do gravitational field. There is this table here where on page 8 where it says original gravitational field strength and mass is reduced to half. How would you do that? Okay, so if you have original gravitational field strength is 6 newtons per kilogram, and you reduce the mass by 1/2. What you guys do, it's so easy to do this, okay? You know your equation is G is equal to big GM divided by R squared. Okay, well, it's giving you G is equal to 6, so you're gonna put the number 6 in for G. It's not giving you the value for big G, so anything it's not giving you the value of, you just put a 1 in. The mass it's saying is half, so you put in for mass 0.5. You don't know what R squared is, so anything you don't know, you just give it a value of 1 and you go 1 squared. So you go 6 is equal to 0.5, right? Because 1 times 0.5 is 0.5 divided by 1, just makes it 0.5, right? And so what you're trying to find though, like, so actually your mass is the x, because this is what you're trying to find, right? So what will the gravitational decrease, increase, or stay the same? So if your mass is reduced by half, what's going to happen to your gravitational field strength here, right? If you have half the mass, that means your gravitational field strength is also going to be half, right? It's also going to be 3, right? Because the mass is half. Remember, the bigger the mass, right, the more gravitational field strength. If mass is reduced by half, then your gravitational field strength will also reduce by half. Okay? So that's how you do that. It's the same thing if mass is tripled, right? It's 3 times more. There's a whole thing on this in your booklet here on page 5. So go fill in your notes. You can try to fill this in. Remember, substitute everything that you don't know with a value of 1, and then you should be able to figure out the answer. Okay? I hope that makes sense. Try to do, there's a practice assignment on Google Forms this week, but like, you guys, here is the answers to these practice problems. Try those for your own practice, and then try the Google assignment that I assigned this week. So this is actually not going to be for homework. This is for you guys to practice to do your Google form, right? I mean, we can try a radius question here, like if you want. So if the radius is reduced, or the radius is doubled, so let's say you have, the original gravitational field strength is 2 newtons per kilogram, and the radius is doubled. So the radius is 2 times greater. Okay, so then you go G is equal to big G M R squared. G is equal to 2 is equal, you don't know the value of G. You just put everything that you don't know as a value of 1. 1. R squared is 2 squared. So that means, right, if that's the case, that means your radius is going to be 1 over 4, right? So your new gravitational field strength is 2 times that number, and you're going to get 2 over 4, which is going to be 0.5, right? So you can see, like, if your radius is doubled, right? If your radius is doubled, you're going further away, right? So, like, if you visualize it, where you have, like, here's the Earth, right? And, you know, here's the object, right? And then you double the radius, and so the object is double the distance. Well, if you increase the radius, the gravitational field strength should decrease, okay? So if you're doubling the radius like that, if you're doubling the radius, then your gravitational field strength should be reduced, right? And so again, when you calculate that, gravitational field strength is big GM divided by R squared. Well, if R is doubled, you put 2 in for R, which means, and your gravitational field strength was originally 2. That means that 2 is equal to 1 over 4, right? Because it's 2 squared. And that means if you're trying to solve for your gravitational field strength, it's going to be 0.5, right? It's going to be half the gravitational field strength that it would be otherwise. Anyways, I hope that makes sense, right? I hope you guys can see how if you increase the radius here, like if you increase the radius, sorry, my board was gone. Like the gravitational field strength goes down. If you're closer to the Earth, the gravitational field strength increases. Okay, anyways, like I said, fill in your notes if this doesn't make any sense. Don't text me, sorry. Email me, let me know. But there's my lesson on gravitational field strength. Okay, bye.